All right, so today we're going to do a review for exam 3. Wednesday is the exam. You're expected to take it in here on your device unless you have made other arrangements with me. There should be no great surprises as to the content, and we're covering everything from exam 2, post-exam 2, until today. For your convenience, I have already uploaded under the readings the practice questions I'm going to go over today. All right, so today's session number is 589151. That's 589151. I should say you are, you might want to bring some scratch paper and like a pencil or pen. I will have to take a glance at it to make sure you haven't like written all the answers on it. But, since there are math-like problems on parts of it and truth tables, that you'll probably want some scratch paper to work those. As I spoke before, you will be allowed to use a calculator. Though I discourage over-reliance on the calculator. My experience is that people overestimate how useful a calculator will be. All right, so we'll start with the inductive reasoning session. We're about to toss 6 coins. What are the odds that all 6 coins are going to come up as heads? All right, so remember each coin has 1 head. So you have a 1 in 2 chance. So this is 1 in 2 to the 6th, or half times half times half times half times half times half. So 2 and 2 is 4, 4 and 2 is 8, 8 and 2 is 16, 16 and 2 is 32, 32 and 2 is 64. Your Odds of all of them coming up heads is 1 in 64, as 67% of you correctly predicted. What are the odds of rolling a 7 on 2 standard 6-sided dice? All right. The equation we used on our first problem was the number of favorable cases, which was only 1, where all the coins came up as heads over the number of total cases. We used the same equation here, but I see that we need to talk about this a little bit. The number of total cases on 2 6-sided dice is 6 times 6. So the denominator is going to be 36. But we need to figure out the number of total cases in which the number of total combinations out of that 36, which would result in a 7. In my opinion, the easiest way to figure this out is to make yourself a chart. As you probably know, on 2 6-sided dice, the combinations that result from the 2 dice range from 2 to 12. But what you may not know, unless you play a lot of games and have analyzed statistics, is the center, most common number that the dice come up as is 7. Why is that? It's because out of the 36 possible combinations, there are 6 different combinations that roll a combined 7. So the correct answer for our question was number 4, 1 and 6, which a plurality got correct, but still most people got it wrong. I will also note the numbers that come up rarely are the ones that only have 1 combination out of the 36 that cause that number to come out. So snake eyes and 12 are the rarest combinations, or the rarest total number, because there's only 1 instance in the 36 that those numbers come up. Which is why if you're about to roll 2 dice in any game, you want to look 7 spaces ahead, or 6 to 8 spaces ahead, and that's where you'll most likely look down. I believe this is also why craps at Vegas is what they say, if you play it properly, will give you the best chances of a appropriate return. All right, how about cards? Playing with a 52 card deck, you have 5 cards in hand, but no aces. What are the odds that the next card you draw will be an ace? Good. So again, the number of favorable cases, how many aces are in a deck? 4. How many cards are in the draw deck? Well, normally 52, but I've already said you have 5 cards in hand. So the correct answer is your odds of drawing an ace are 4/47. All right, so we will do some of the inductive reasonings. I didn't throw, I did not do a practice example using the gambler's fallacy. So just in case I'll just say it verbally. If I ask this question, don't fall for the trick answer. The trick question is this. You have tossed a coin 5 times. It has come up heads every time. What are the odds that it will come up heads the next time? The correct answer is 1 and 2, 50%. Because the coin does not care how many times it has already come up as heads. Don't confuse that with the you're about to toss a coin 6 times question. What are the odds that it will come up heads all 6 times? 2 very different questions. All right, so we'll do some of the inductive reasoning. We'll do some translations. The statue isn't by either Cellini or Michelangelo. Good. Yeah, the negation happens before the either, indicates that it's going to be outside the parentheses. And then an either or indicates a wedge. Yeah, really 2 is the only one of those it could be. If I don't have either $2 in exact change or a bus pass, then I won't ride the bus. All right, let's talk about this. First of all, you should never choose anything that looks like number 1. What's wrong with number 1? You need, whenever you have more than one letter, and especially when you have more than 2 letters, you need parentheses to clarify the priority of the relationship. So 1 is not properly formed. That cannot be the right answer unless the question is which of these is not a properly formed equation. All right, so let's translate this. If tells me to open a parentheses. I don't tells me I need a negation. Have either tells me to open another parentheses. $2 or a bus pass. Since I have 2 letters there, I have to close the parentheses. Then I won't ride the bus. Comma indicates this can be separate. Won't indicates a negation. And ride the bus, R or B. I guess we can't do B because we already used B for bus pass. But that's got to be the right answer. Yes. Counting the negations help. Did I only give you 2 options that had? I only gave you 1 option with 2 negations. So yes, that would be a nice, good, a clever strategy. So yes, since there's only 2 negation words, And none of the top four can be correct because those all include three negations. So yeah, good catch. All right, I'm going to Rome or Florence, and you're going to London. Sounds like everyone's having a better spring break than I had. I went to Raleigh, North Carolina. Yeah, good. I guess that needs no explanation, 100%. Very nice. All right, so here, for the next set of problems, so there's going to be some translations. Then for the next set of problems, we're going to have identify the truth value of the complex statement, the compound statement, assuming A's and B's are true, X's and Y's are false. Good. Yes, this one is false. We have an or statement is the major operator here. The right side is going to be false because these two don't match, because the Y is false and the A is true. On the left side, the B is going to be true, making the or true. So we've got true on the left side of the arrow. The X is false. So we've got true on the left, false on the right of the arrow, making that side false. Both sides of the or are false, making the statement false. All right, next one. All right, well, let's take a look. So the left inner parentheses, both are true. In the right, the left side's true and the right side's false. This arrow is true. This arrow is false. This arrow is false. Then we apply the negation. It's true, as 73% recognized. All right, let's do, so there'll be some plug in the values. Tell me what the value of the statement is, given the set values for A, B, X, and Y. Then we'll do some tests for validity. So tests, if R, then S, S, therefore not R. Test that for validity for us. Yeah, it's invalid, and you can see that when both are true. So let's plug in some values here. All right, so anytime S is false, that can't give us an invalid set of values since we need all premises to be true. Anytime R is true, anytime R is false, the conclusion is true, and when R is true, the conclusion is false. So that second set of values can't give us an invalid set of values. But when both are true, the R, if R, then S is true. So therefore, both premises are true, but the conclusion is false. Yes? What's that? Of course. Did you get the right answer? Then definitely. Did it go quicker than what I did up here? Yeah, cool. So yeah, you'll note I didn't tell you whether you had to do truth assignment or truth table. Do the one that works best, either for you or for the problem. Although I do note that certain sorts of problems are much easier with one rather than the other. So, and I will try to put both on the test. All right, test for validity. This one takes a little bit longer, doesn't it? All right, well, let's see what it looks like. I'll start with the conclusion, plug in these values. All right, so anytime the conclusion's true, it cannot give us an invalid set of values. So we need to focus on these top two cases. We'll look at S, right? In the first instance, where S is false, that cannot give us an invalid set of values. So all we need to do is look at this when R is false and S is true. When R is false, this outer, not R, will be true. which makes the or true. And that will be our invalid set of values, as 69% of you predicted. Would it help if I also did it with truth assignment? Yeah, why don't I take a minute and do this one with truth assignment as well. All right. All right, so remember, truth assignment, we want to set this to an invalid set of values. We set R to false. We set S to true. And then we can see immediately again here, since that R is false, it switched to true, which makes the or true, which makes premise 1 true. You know, you could use either way. Yes? Oh, sure. All right, so what we have here is we set the conclusion R to false. We set the premise S to true, and we plug those in. We're looking at this or in particular. This R starts off as false, gets switched to true. It's going to make that or true no matter what happens over here. Makes this premise true, and therefore the problem is invalid, and the values are false as true demonstrates it. So you could use either. That was the sentence I think that I mumbled. So you could use either way. They both get you the same result. I note that truth assignment works really well when you've got only one compound statement that's sort of wacky like this. Truth assignment is a lot harder to do when you've got more than one statement that looks like this, in my opinion. Okay, so we'll have a section where T's are true, F's are false, and certain variables will be unknown. What is the value of the whole statement? Is it true, false, or unknowable based on the information given? Good. Yeah, that one's known because when the not F is going to be switched to a T, which makes the left half of an and a T. So when the U is true, the end will be true, but when the U is false, the end will be false. So you can't know the value of the statement without knowing the value of U. What is the value of if U then not F? Yeah, this is, since the not F gets the negation switches it to true, Since the right half of the error statement is true, no matter what happens on the left, this will always be true, as the 87% realized. All right, what about this monstrosity? It is not the case of if you, then both T and F or T. All right. This one, I mean, there's a hard way to do it and there's an easy way to do it. I will show you the easy way to do it. The easy way to do it is to look at the outermost operator. The outermost operator is an OR. We have an OR with a true next to it, which means no matter what happens in these other sets of parentheses, that OR is going to end up being true. So then at the end, we negate it to false, as 62% saw. And of course, the long way to do it was to work all this out inside, where the AND is false, the U will sometimes be true and sometimes be false, which means the arrow will sometimes be true and sometimes be false, which means this OR will sometimes be true and sometimes be false. But then we get to this one, the left side will sometimes be true and sometimes be false, but the right side will always be true. Therefore, the OR is still true. Oh, but then it gets negated to false. Okay, and there'll be some good S rules on there. What can we conclude, if anything, from both A and B? And I didn't set this up as multiple choice, but you should write it out. And of course, from any AND statement, such as A and B, you can get the truth of both halves of the AND. In this case, A as well as B. How about from negated A and B? What, if anything, can we get from that? From negated A and B on its own, you get nothing. Nothing can be derived. Now, if, in contrast, I'd say not both A and B, and I added a second premise A, from that, you could get nothing. But negated both A and B, you can't get anything, can't drive anything. All right. What about if not A, then B, and the additional claim A? Oops. All right, from that, you get nothing. Because with an error statement, you either need the exact match of the left, which would be negated A, but we don't have that, we have A, or you need the opposite of the right, which would be negated B, and we don't have that, which would give us the opposite of the left. But from the opposite of the left, you can't derive anything. All right, what about from if A, then not B, and the additional claim B? All right, so here again, we have error statements. We can get an inference if we can match the left. We can't do that. Or if we have the opposite of the right. Since we have the opposite of the right, we can infer the opposite of the left. How are we doing? Tomorrow night, online, there is a tutor-led review. I've already sent you the link and an announcement. The test will be 30 to 40 multiple choice as we've had here. Any more questions? Yes. I think so. I mean, I'm not going to try to surprise you, but I mean, there will be an occasional something that looks like this, or that looks like this. So, I'm certainly not promising that everything will be easy, but I'm not going to try to, throw you something radically different from what I've suggested here. I mean, I might give you a truth table problem that's got two compound statements, not just one. I might do that, or one that has three variables. But again, but that would be like the hardest one in the section. I'm not gonna, it's not all gonna be like these hard.
So just for clarity on the if then statement, it has to match exactly the left or the opposite of the right.
Right.
So if it matches exactly the left, then it's exactly the right.
Right.
If it matches the right, it's opposite of the left.
If you get the opposite of the right, you get the opposite of the left.
Okay.
So this isn't a match because the negation is different, but that's the opposite of, which is what we want. And therefore you get the opposite of the right. So something like this could be, if anything is a dog, therefore, if anything is a dog, therefore it cannot be a cat. This is a cat, therefore it cannot be a dog. All right, well, good luck. See you next time.